Here we're starting on section 1.7, which is going to take us back to the topic of functions, but go a little bit deeper into some of their properties. Let's start out by considering a function f from the set S into the set T. We have two new definitions for this function. One of them is called one-to-one. A function f is called one-to-one if distinct elements in S have distinct images in T under F. And there are two ways of stating this by definition. One of them says that if x1 and x2 are elements of S, and x1 is not equal to x2, then f of x1 is not equal to f of x2. One way this might be interpreted is if you have two distinct elements of the domain, they're not equal to each other, then their images under f must also not be equal to each other. The values in which the function gives them must not be equal to each other. This could also be stated as if x1 and x2 are elements of S, and f of x1 is equal to f of x2, then x1 must be equal to x2. The next definition for f is something called onto. A function f is called onto a subset of B of T if B is equal to the image of f. F maps onto T if T is equal to the image of f. And one way we can state this by definition is to say for each y, an element of T, there is at least one x, element of S, such that f of x is equal to y. Another way of viewing this is if you have an element of the codomain T, and there's a element from the domain S which maps to it for all the values in the codomain, then we call it onto. So basically, onto functions do not miss any elements into the set in which they map into. They map to every element within the set. So here are some illustrations for what we mean by onto and one-to-one. An onto function will take each element of the domain and map them to elements in the codomain, and every element in the codomain will have an element mapped to it. So here everything in this side on the right gets something mapped to it from the domain. And that's what we call onto. There's no missing elements in the codomain that are not mapped to. And then one-to-one means that every element in the domain gets its own unique element in its image or inside of the codomain. Now we can miss elements here when we're talking about one-to-one, but each element of the domain gets its own unique element in the codomain. One-to-one and onto means that each element of the domain covers each element in the codomain, like so, and each element in the domain is assigned its own unique element in the codomain, and there's no sharing between different elements from the domain. So in the first example, just to clarify also, this one is not one-to-one. Even though it's onto, it's not one-to-one because these two elements in the domain share a common element in the codomain. So let's look at two specific examples and discuss whether or not we think there's any one-to-one and onto mappings from these sets. The set S contains the elements 1, 2, 3, 4, and the set T contains the elements A, B, C, D, and E. Now first off, we can construct a one-to-one mapping if I take 1 and map it to A, 2 map it to B, 3 map it to C, and 4 goes to D. Now this would be an example of 1, 2, 1 mapping. However, it's impossible with this to do a onto mapping. The reason being, there's no way for me to map to E using elements from S. And while I could say, oh, I'll just go ahead and send 4 over there as well, that doesn't work in the concept of a function. In a function, you can only have one mapping per element in the domain. So that would not be possible with a function. So one of these is always going to be left out if I'm creating a mapping. Now, if I was to eliminate E from the codomain, from the set T, then what I have here would be onto. I would get everything within the set T. But just as it stands from the beginning, there's no way of creating a onto mapping. So let's look at some examples and determine if these functions are one-to-one and onto. Let's start with the function from the real numbers into the real numbers given by f of x is equal to x squared. Do we think that this is first off one-to-one? If that's the case, what we would be thinking of is it possible to plug in two numbers for x, two different numbers, and get the same number out for both? Well, for instance, I can plug in -2, and that would turn into -2 squared, or +4. And that's the same result that I would get if I plugged in 2 squared, and it's 4. So this means for two different numbers for x, I get the same number out as a result. So by definition, we view kind of like this. Since our two x's are not equal to each other, x1, x2 not equal to each other, however, the functions are equal to each other, then we know it is not one-to-one. So the next question is this onto? Well, keep in mind that we say that this is a function from the real numbers into the real numbers. So is it onto? Well, is it onto the real numbers is another way of stating this. Does it cover the whole real number set by this function? Not exactly, since f of x equals x squared only takes values on the interval from 0, including 0, to infinity. It never covers anything less than 0. It is not onto the full real number set. It is, however, onto just that interval from 0 to infinity, however, since it takes and maps to every number within that interval. So we can say it's onto a certain interval, we just can't say it's onto all the real number set. Let's go back to our function, characteristic function, which is equal to 1 for x element of A or 0 for x element of S complement A. So this type of function had only two values, 0 and 1. And so we can say as a function, this is onto the set 0 to 1. However, it is not one-to-one. The reason why it's not one-to-one is several elements can be assigned to a 0 or a 1 at the same time, since most of the time we have several values within our sets. So to kind of summarize it, I'll say that it is not one-to-one in most cases, since the elements of A all take the same value of 1. It goes against the definition of one-to-one, so we can't say that it would in most of the time, unless there's just one element within A. But if there's several elements in the set A, then it will not be one-to-one. Before proceeding too much further, let's talk about something called the inverse. The inverse of a function f from s into t is a function denoted with this f superscript -1, which goes the other direction from t into s, such that f inverse of f of x is equal to x for all x element of s, and f of f inverse of y is equal to y for all y in the set T. What's important to know about inverses is we only have an inverse. In other words, a function f is invertible if and only if it is both 1-to-1 and onto from S onto T. Now let's consider this function f of x is equal to 3x minus 5. I want to start off by considering the 1-to-1-ness of this function. Now this function is 1-to-1. If we plug in a value for x, if you take two different numbers, all the time you'll get out different things from the function. How do we prove this by definition? So here's how I actually prove that a function is 1-to-1 by its definition. We start off by saying let x1 and x2 be an element of the domain, in this case the real number set, such that the values f(x of 1 and f of x2 are equal to each other. Then, as a result, we take a look at the function, and I'm going to plug in x1 and x2. Then 3x1 minus 5 should be equal to 3x2 minus 5. Now if I solve this down for the x1, x2, I'm going to add over a 5. We'll have 3x1 equals 3x2. And if you divide out the 3, it'll say that x1 is equal to x2. And this verifies for us that it is 1-to-1, since the two values of x are now equal to each other, coming from the fact that the function values are also equal to each other. Thus, this is a demonstration that f is 1-to-1. Now, to demonstrate that it's onto, and if we know it's 1-to-1 and onto, then we can talk about its inverse. What we're going to do is let y be an element of the codomain, in this case, the real number set. So what we want to do is we want to find an x such that y is equal to f of x. If that is true for all values of y, then we have an onto function. Thus, what we're going to be looking at here is y equals f of x, and so y is equal to 3x minus 5. What I'll do to make this happen now is solve for x. And if we solve for x here, we'll get x is equal to y plus 5 over 3. As a result, what we have here is if we were to take f of this x here, which would turn into f of y plus 5 over 3, that would be equal to 3 times y plus 5 over 3 minus 5, which when simplified would be equal to just y. And this shows us that given this value for x, we have a value for y. And so we can say that f is onto the set of all real numbers. This also tells us about the inverse now. Since we've solved for x here by doing this up above, that also tells us what our inverse would be as well. If we were to take the x equals y plus 5 over 3 and swap x and y, we would have y equals x plus 5 over 3. And so what this refers to is the inverse. the inverse would be given by f inverse of x is equal to x plus 5 over 3. So once we know that a function is one-to-one and onto, we can simply take what we've done up above, solve for x, and we can find the inverse. So the basic steps would be to solve for x and then swap the x and y. Now let's look at this situation here. We have a function f of x equals the square root of x minus 2. I'm going to go ahead and go through this process of verifying that this is one-to-one. So to do that, what I'm going to do is I'm going to let x1 and x2 be an element of this case, the domain 0 to infinity. We'll say that and we want to assume that f of x1 is equal to f of x2. Then we know that the square root of x1 minus 2 should be equal to square root of x2 minus 2. If we add the 2 over, square root of x1 equals square root of x2, which should tell us that x1 is equal to x2. As a result, we can then say, since we can manipulate it into this form, we can say f is one-to-one. Now for onto, we need to make sure that we say up above that this is a function into the real number set. But we should also recognize the square root function will never take any negative numbers. So it's not going to actually be onto the full real number set. So we'll only consider onto-ness for a smaller set. So what I'm going to do is let y be an element of the interval from 0 to infinity. Then we'll look at y equals f of x, and what that means is we'll have y is equal to square root x minus 2. And what I'll do is I'll go ahead and solve for x. So if I add the 2 over, we'd have y plus 2 equals the square root of x. And then if I square both sides, we'll solve and we'll say x is equal to y plus 2 squared. So since I can solve for x here within this interval, we know that it's going to be onto the interval from 0 to infinity. And the inverse, if I swap the x and y, we'll have y is equal to x plus 2 squared, which means to us that the inverse function f inverse of x is equal to x plus 2 all squared. On the interval, and we want to make sure to be very clear about this, that we're only using the interval from 0 to infinity. Now, one more situation here, we're going to consider a function to check to see if it's one-to-one and onto. Here it's a function g from the product of the integers cross the integers into the product of the integers cross the integers, given by the function g of n comma n is equal to the ordered pair of negative n comma negative m. So first off, let's consider whether or not we can show and prove that it's one-to-one. So what I'm going to do is I'm going to let m1 comma n1 and m2 comma n2 be an element of the integers cross the integers, such that g of m1 comma n1 is equal to g of m2 comma n2. Then, as a result of this, we should have negative n1 comma negative m1 n1 is equal to negative n2 comma negative m2. And by the nature of ordered pairs, we should be able to say then that negative n1 is equal to negative n2. That is, the first part of the ordered pairs here are equal to each other, and we should be able to say the same thing about the second parts of the ordered pairs. That is, negative m1 is equal to negative m2, and thus n1 is equal to n2, and m1 is equal to m2. And so since we can show this is the case, it tells us that it is 1-to-1. Now let's consider on2. And we'll think about it just a second before proceeding. Do we think that if we plug numbers in for m and n, the numbers we get out will cover all of the range of ordered pairs with integers? Should be the case, because if I plug in a positive number for m's and n's, I should get out negative numbers, but if I plug in negative numbers, it's going to turn back into positive again. So it should cover the values across all the ordered pairs with integers in them. But to show that's the case, I'm going to walk through the full steps of verifying that a function is on2. The way we're going to do this is we're going to let p comma q be a member of z cross z. What we need to do is we need to find an mn from within the product z cross z, such that if we take g of mn, it'll equal to p comma q. So let's see how we can make that happen. If we take m equal to negative q and n equal to negative p, g of m comma n would equal to negative n comma negative m, but that would be equal to negative negative p comma negative negative q, which would be equal to p comma q. And so that verifies that g is onto z cross z. Now the last thing we're going to talk about for functions, and specifically with their inverses and so forth, is the image of a set and the inverse image of a set. So let's start out with a function that maps from S into T, and then let's take a subset of our domain called A. So A is a subset of S. We use this notation for the image of the set A under F. F of A is equal to the set of all f of x such that x is an element of A. And the inverse image of a set B and T is given with this f with a subscript little arrow pointing to the left. The inverse image of B is equal to all x and S such that f of x is an element of B. If f is invertible, then the image set is equal to the same thing as f inverse of B. So it doesn't necessarily have to have a inverse or be invertible for us to talk about its inverse image. It's just kind of going backwards from one set to the next. But if it is invertible, then f inverse of B is equal to the inverse image of a set B. For y element of T, rewrite the inverse image of y for the set inverse set of the singleton set of y. So it might help to kind of go through an illustration of what these things are meant to represent. So let's take the set S for our domain, but let's take a subset of that called A. If I take each x in that set and then map it to where it exists within the codomain T, I take the whole set A, then it'll have its own image within T, which will be called f of A, and contained within there will be all the f of x elements that get mapped by the function. Now the inverse image, though, we take a set B and we take all the f of x elements in there and go backwards to where they started from in the original domain. So if we look at all the x values in the domain that mapped to that set B within T, then we'd be talking about this set here, which is called the inverse image of the set B. Okay, so let's look at a few examples of how we apply these image sets and inverse image sets as well. Starting with this function from the real numbers into the real numbers given by f of x is equal to x squared. We want to start by finding the image of the interval from 0 to 3. Now basically what this is going to do is take each element within this interval and process it through x squared. So if we were just to take a look at the endpoints of this interval and plug those in for f, say like f of 0 would equal to 0, f of 3 would equal to 9, then our interval inside or after working it through the function would actually come out to be the interval from 0 to 9. So that's actually the image of this interval under the function f. Let's consider the inverse image of the set from 1 to 9. Let's consider this by definition here. It means that it's the element of all x and r such that 1 is less than or equal to x squared, less than or equal to 9. But this is also equal to all x in the real number set such that negative 3 is less than or equal to x less than or equal to negative 1, or 1 less than or equal to x less than or equal to 3. And you can verify that's the case because when you square through by everything here, if you were to square all the numbers, you get back to the interval between 1 and 9. So we had to kind of work our way backwards to what it could be. Another way of doing that is if you took the square root of 1 less than or equal to square root x squared less than or equal to square root of 9, you'd have to consider it with a plus or minus square root. So you get a plus or minus 3 and plus or minus 1. And so this is actually going to involve two intervals. The interval between negative 3 and negative 1, and also the interval between 1 and 3. If you were to take the numbers in either of these intervals and run them through the function, they would both map into the interval from 1 to 9. Let's consider the inverse image of the interval from negative 1 to 0. So what this would stand for is the set of all x in the real number set such that negative 1 is less than or equal to x squared less than or equal to 0. Now the issue here is x squared is never a negative number. So there's really no values of x here that satisfy that inequality except for one number, and that's 0. So this is really just going to be the singleton set of 0. Now in this next one we're going to figure out the inverse image of the closed interval between negative 1 and 1. This stands for the interval where we have all real numbers such that negative 1 is less than or equal to x squared less than or equal to 1. To verify the reasoning behind this one, let's at least think of it graphically. So what we're dealing with here is the function x to the second power, which is the parabola. So y equals x squared has that shape. And when we talk about this interval between negative 1 and 1, it's coming from the image, or the range, is another word for it. and what part of the function for its x values is mapping into that interval. So if we look at our function between -1 and 1, values of our function is going to fall between, in this case, -1 and 1. None of the values are going to dip below, but they still fall inside of that interval. So when we say this inverse image of -1 to 1 is going to also be the closed interval from -1 to 1. Now let's look at one more function here that says this is the function that maps from the integers into the set -1, 1 given by h of n equals -1 to the n. We want to start out by finding the inverse image of 1. So thinking about it, what values of n, let's think about it here. This is n within the integers such that -1 to the n is equal to 1. So what values of n, or what kind of numbers I should say, would we have to raise -1 to get to +1? Indeed, n must be an even number in order for it to turn to a +1. So this set is equivalent to the set of all integers such that n is even. Similarly, if we wanted to look at the inverse image of -1, then that's all n in the integers such that -1 to the n is equal to -1, which means we must be looking at odd exponents for n. So this is equal to the set of all n in the integers such that n is odd.